Hey, Algebra 2 Honors students, it is a beautiful Friday afternoon, scary beautiful for February in Philadelphia. But the purpose of this video is to help you in becoming very efficient in solving quadratic equations. Okay, so as you know, we're going to get started with solving all sorts of quadratics. So in class, we've already talked about completing the square, and in the past, we've talked about factoring. The quadratic formula we've kind of touched on. Okay, and there's a fourth method just called square rooting. For lack of better words, that also would be a nice method to have in your back pocket. So I'm going to go over 4 examples today and describe to you when and how you know which method is probably most efficient. Although you can use completing the square or the quadratic formula anytime, it's not going to be the most efficient method to do every problem. All right? So we'll start with an example where we can use factoring. All right? So let's say the instructions were to find the roots of this polynomial, all right? 5x squared, let's say, minus 17x plus 6. Well, finding the roots of that polynomial would be the same instructions as solving that equation, right? So let's just, you can really use either set of instructions, okay? So solving that equation. This is an example of something that I would use factoring, okay? Now, it's not obviously factorable. All right? When the lead coefficient is not 1, we can't just find 2 numbers that multiply to 6 and add to 17. No, you can't do that when there's a lead coefficient other than 1. All right? So, but the way I know this is factorable, in fact, I created a problem that I knew would be factorable, is that if you multiply the a value and the c value, all right, in this case the 5 and the 6, and then 5 times 6 is 30, of course, and then ask yourself, are there 2 numbers that multiply to 30, so there are 2 factors of 30 that can add to negative 17. If the answer is yes, then the problem is factorable, okay? Yes, the answer is yes in this case because the 2 numbers that multiply to 30 and add to negative 17 are negative 15 and negative 2, right? Because they exist, this problem is factorable, okay? So I hope you caught that. That's how we know, in fact, the problem is factorable. It takes about 15 seconds. Just figure out, are there 2 numbers that multiply to that product and then add to the middle term. Right? Now that we know it's factorable, we can factor it. Now, using guess and check is always a good move. Okay, 5 is a prime number, so it's going to be pretty easy to guess and check. But let's do it a different way. Let's split up a middle term. I believe we did this in September, but as a little refresher, the way we factor this by splitting the middle term is we use those 2 numbers that we just found. Right? Negative 15 and negative 2 would multiply to 30 and would also add to negative 17. So I'm going to split up the middle term. Instead of writing negative 17x, I'm going to write negative 15x and negative 2x, and then drop down the last term. So I'm making a problem, turning this trinomial into a polynomial with 4 terms. Okay? Now, I didn't have to write it in this order. I just thought it would be easier because I knew 15 was a multiple of 5. Okay? The next step is going to be to take out the GCF of each of these 2 groups of terms. So in a sense, we're factoring by grouping, if you guys remember how to do that. Take out a GCF of 5x here, we're left with x minus 3. Take out a GCF of minus 2 here, and we're also left with x minus 3. Right? If we're factoring by grouping, what's in these parentheses has to be identical. Okay, just to remind you from the past. And now if we factor out that common factor of x minus 3, we're left with 5x minus 2. Now, once we know the factors, we can use the zero product property. If x minus 3 times 5x minus 2 is 0, then either this factor is going to equal 0, so in this case x would equal positive 3, or this factor would equal 0. And if you can't do that in your head, just set this factor equal to 0 and solve it. You would add 2 and divide by 5 to get 2/5. So there's 2 solutions, positive 3 and positive 2/5. We write them like this. Okay? So the roots of this polynomial are 3 and 2/5. That is using factoring to solve this equation. Could you use completing the square? Yes, that would be a terrible idea. Look at these numbers. All right. Quadratic formula would probably be my second suggestion for this problem. Okay, so that's an example where we use factoring. Let's do one now where I would use completing the square we just handled. All right, but let me just, so we don't have to do a whole problem, but let me just show you how I could manipulate this problem a little bit and give you an example of one where I would use completing the square. All right? This problem here would be an example of one where I would use completing the square. Why? Well, because b is even and a is 1. All right? This obviously can't be factored. The lead coefficient is 1, so we can just ask ourselves, are there two numbers that multiply to 6 and add to negative 10? No, so it can't be factored. So the next line of business would be to use quadratic formula or completing the square. I like completing the square because it's just not as messy. Completing the square is helpful when b is even. If b is odd, we've got to incorporate some fractions. It gets a little messier. All right? So this is an example of where I use completing the square. I won't actually do it. All right? If we now just change this and make this a, well, I'm not going to make it a minus 7 because that would be factorable. Instead of making it a minus 4, minus 4, I would still use completing the square. Well, let's make it a minus 3 then. Okay? This is an example of where I would just concede and use the quadratic formula. I'm calling the quadratic formula a concession because it's an ugly formula. It should really be a last resort. Okay? So if this problem is not factorable, b is not even, so okay, I would use the quadratic formula. Quadratic formula says this. Again, we already derived it, so you really have to either memorize it or be able to derive it on a quiz. Right, but that's the quadratic formula. So we can just plug in these values. The opposite of b is going to be positive 3, plus or minus. The number under the radical, as you guys know by now, is called the discriminant. Okay, the discriminant in this case, b squared minus 4ac. Do the subtraction last, just to be careful. B squared is going to be positive 9. 4ac is 4 times 1 times 6. So 4ac is 24. So then we have 9 minus 24. Right? 9 minus 24 is going to be negative 15. Right? B squared minus 4ac is negative 15. A lot of folks mess up the discriminant, so just be careful. From this step, we already know the nature of our solutions is going to be imaginary. Right? The solutions will be imaginary numbers over 2a, so over 2. This is not completely simplified yet. Let's do this. So the square root of negative 15, as you know, is I root 15. So we could leave our answer like this. That would be an acceptable solution. Or we can write this in two fractions. This is probably a little more common to write it as 3 halves plus or minus root 15 halves I. That's probably a more common way of writing the solution than just leaving one single fraction, but I would accept either of these two. Okay? So we've gone through very quickly. We went through an example where I used factoring. We went through, at least I showed you an example of where I would use completing the square. We didn't actually do it because we just did that in class the last couple of days. Here's an example of where I would use the quadratic formula. And there's one other method I wanted to go over, which doesn't really have a name. I just call it square rooting because that's the main step. I would recommend using square rooting whenever the b value is 0. X squared plus 6 equals 0, I would use square rooting. But let's do one that's a little more challenging than that. Let's do, let's say 9x squared plus 5 equals 11. Okay? There's an equation where I know it's not equal to 0, but we know the b value is going to be 0 because there's no linear term in the equation. There's no x in the equation. If you're using square rooting to solve, which I would do in this case because there's no x term, you want to get the x squared by itself, and then you square root both sides. Right? So you want to get 1x squared by itself and square root both sides. Take away 5 and you get 6, so we have 9x squared is 6. Now divide by 9, so x squared is 6 divided by 9, which is going to reduce to 2/3. Okay, so x squared equals 2/3. And now we square root both sides. Don't forget to use a plus or minus. All right, so we get x equals positive or negative, the square root of 2/3. Now, we haven't gone over rationalizing the denominator yet in this class. But you would never leave a fraction under a radical. So you might remember this from Algebra 1. Instead of leaving the square root of 2/3, we would write this as, forget the plus or minus for now, that'll be in the answer. But we break it up into the square root of 2 over the square root of 3. All right? Unfortunately, we're still left with a radical in the denominator, which you're technically not allowed to have in a simplified answer. So what we do is we multiply the top and bottom of the fraction by that square root, by root 3. And now we end up is root 2 times root 3 is root 6 over root 3 is 3. So the best answers would be plus or minus root 6 over 3. Those would be your two solutions, okay? So this is an example of an equation where I would use square rooting, all right? Because, yeah, I mean, of course, you could subtract 11 and then use the quadratic formula. That's totally fine if you like that better. But this kind of a method is very nice whenever you don't have an x term. You don't have a linear term in your problem, all right? So whatever, 4 different methods to solve a quadratic. Sorry the video got a little bit long, but have a nice weekend, and I'll see you on Monday.